Good afternoon, ladies and gentlemen. My name's Tommy White. I'm one of the developers of the MasterSeries. Today we're looking at concrete design, and in the MasterSeries we cover concrete in quite a lot of different areas. We have simple beams, we have flat slabs, we have columns, pad foundations, we have pile caps, and we have retaining walls. What I'm going to be looking at today is frames. So the first thing I want to do is just to minimize this website, and we're now into the MasterSeries. So this is the MasterSeries program, and I can see first of all that I'm running a 2013-12 edition. So let's look at MasterFrame, our core program for handling frames, and let's look at some of the samples. So we're going to be looking at this concrete plain frame initially, just because it's easier to see and understand than a complex 3D frame. We can also look at obviously a 3D frame as well. We can do quite large frames in concrete if you so desire. We can also do individual beams, and there's no reason why we can't do, I don't know what this one is, as boring, ground beams. We can do ground beams if you're doing domestic work. Ground beams, no problem, as you can see, and you'll find there's probably piles at one or two of these points and the likes. We also are able, quite simply, to take any steel structure and interface with that and do the concrete foundations, or even the ground beams and the concrete pads at the same time. If you wanted to put in the ground beams along the runs to support your walls, we can do that for you in the design. So let's get back to this first example, and I'm not going to generate the frame because that's a different webinar. What I am going to do is I'm going to look at this frame. So first of all, it's a traditional plain frame, except we have some columns offset. We need to have wider spaces down below than up above, so we actually have these quite awkward little columns coming in the middle of beams, and beams then are columns stopping underneath beams as well. If we turn it on to 3D, we will see that we have quite large beams here, and then we have smaller beams. I'll just turn off my node numbers. We don't need to know about those. And if I just rotate the frame into 3D aspect, we'll see in fact that we've quite our large T-beams, and then in the top, and this is only to demonstrate what we can do in the MasterSeries, we have inverted the T-beams. So it's going to be inverted T-beams with probably precast units onto the bottom flange of those inverted T-beams. So we'll just look now at the frame, and we'll just look at going into the editor. We have our loading on our frame as normal, and I'll just drop back to turning off the 3D. We don't need the 3D anymore. So we have some loading, and again, I probably don't need for this purposes to see all the numbers, but we have some UDLs, a trapezoidal load, some partial UDLs, and I'm probably sure we might have a point load there somewhere. No, we don't. Doesn't matter. If we look at the frame in detail, I've set up some loading cases, and the first loading case I have is dead plus live plus on all spans. That's the first one. The second one is dead plus live on alternate spans, and we'll notice here that we don't go maximum min max min, because it's the span that's important, not the subdivisions. So therefore, to get the maximum sagging moment here, or in this case the minimum, we have minimum all through, and then obviously when we go to the alternate, we will have the maximum on all three components of that to give you the maximum effect on that span. We're able to do that because we work with load factors. We work with load factors for each load, and we will look at that in a moment. So that's my three principal cases: my all spans loaded, and my patterned loading, my alternate 1 and alternate 2. Now I'm just going to bring across a publication which I'm sure you've all had a good look at in the past, and this is from the Concrete Center, and it's on EuroCodes. And if you look at the loading patterns that are possible in EuroCode, you can either work with load set 1 or load set 2. We in the UK normally work with load set 2. Load set 2 is the all spans loaded, which is what I did, and is this one here, plus alternate spans loaded here. Now, the difference between the BS and the EuroCode is quite significant, and I've highlighted here. And that is that the value of gamma G should be the same throughout. So the dead load on all alternate spans is the same value throughout. So it's maximum, minimum, maximum, minimum for the live loads, but it's just maximum for the dead loads. So that is different to what we did in the BS, where we had minimum 1.0 dead load. That's worth noting. So we will be adopting these two loading patterns. Now you could yourself go in and do the adjacent spans loaded. And statistically the difference in the support moments you get from this is very minuscule compared to just all spans loaded. And that's why in the UK we recommend you don't do it. The other reason is that when you're dealing with large frames, this is going to generate n+1 loading combinations. So in a very complex frame, you will be dealing with a colossal number of loading cases and will be very, very complicated. It's doable because in the MasterSeries you're able to create up to about 160 different load groups. So you could create yourself that number of load patterns, but with a lot of work. So we're not going to do that. Now, I'll just close this document or minimize it at least, and let's go and look at these values. So let's go into the loads and the loading combinations. So loading case 1 is 1.25 and 1.25 and 1.25, and strangely we're looking at loading case 2 in our it might help if we try and get this all looking the same. Come back to my editor, that's better. So loading case 1 is all spans loaded, maximum, and you'll notice we're using the 1.25 because we're using this at the 0.925 modification factor that you're allowed to do. Naturally, you could go in and edit and tell it which load groups you want to be for storage and use the 1 rather than 0.925. What I've done is I went into my design codes, and for the EuroCode there's obviously a national application document for every country, and we give you the default EuroCode values and the UK. I've gone in and created two additional ones, one for Ireland, which is more or less the same, with one or two little changes in some of the values in the design parameters, but also I've created a UK one where we physically use 1.35, and that's quite easy to do, and I will come back out and show you how to do that in a wee while. But I'm going to stick with the 1.25, which is the standard, so we can say yes, we're happy with the UK ones, so it just comes straight out. So that's loading case 1. Loading case 2 is maximum all spans dead, but only maximum live load on odd spans, and likewise then on even spans is the next case. We then have some serviceability cases, and they're created so that we can do our foundations. Although to the EuroCode you probably don't actually need them anymore because everything's done to Ultimate anyway. That's the point. And then we have the same things again, and the reason for having these again is that we also, just like in steel, have to do equivalent horizontal forces, or as we called it in the British, notional horizontal loads. So let's have a quick look at that. Loads, special loads, horizontal notional loads. So coming back, what we're saying is in case 1 we want to take 0.5% of the vertical loads and apply them horizontally at 0 degrees. Case 2 we want to take again 0.5 at 0, and case 3 0. So through the service cases, the case 7, and we're now repeating ourselves, but we're applying the notional load at 180, i.e. not positive x, but negative x direction. So we're going from right to left. And then we repeat that for the next 2 cases. So we create 2 copies so that we can do this. If we had a very symmetrical frame, we wouldn't need to worry about doing it in both directions because there would be no increase. Now, interestingly, and I was just reading up on this morning, you don't really have to do this just for the beams. It's really for the columns that we're interested in these notional horizontal loads because they have only a small influence on the beam support moments. It's the columns that they actually put the additional moments into. And we'll be able to see, looking at the left and right directions, whether we do get a change in the forces that's significant. The next thing is that you can, having done all your analysis, go and assess your frame to see whether or not it is sway sensitive, just like in steel design. And if it is, then apply a second order analysis. Well, we are of the opinion if it isn't sway sensitive, putting P delta onto it in the first place is going to do no harm. And if it is, it's going to be what you required anyway. So having said that, you might as well go and put it on. So it's not under loads, it's under an options, analysis options, and we have now told it to do P delta. So I've already set this up on loading cases, and if I just go in, I'm going to use the Newton-Raphson method. The geometric stiffness is really for steel structures, and we're going to put the P delta on the ultimate cases because again you only need to do that on ultimate, not service cases. So that's everything set up to analyze and design. So I am going to analyze this, and as I go to analyze, you'll see that we're getting a confirmation that we've got P delta turned on and we've got the notional horizontal loads turned on. We haven't created any plastic hinges, there's no seismic or dynamic analysis, and we just say go. So plane frame, and that's it, done very, very quickly. So I'm just going to come back out again before I go in to the concrete design, and I'm just going to take you through this customization of your Eurocodes. So we have our countries, the default and UK, and we can now create additional ones. If I go to the UK 1.35 and I look at the actions on structures, there's nothing there. If I look at partial load factors, here we go. We have gamma as 1.35, which we have anyway, but we don't, this little funny symbol, can't remember the name of it, is 1. Whereas if I go back and look at the BS version, oops, wrong button again, we'll see that this is 0.925, which brings this down to 1.25 in those cases. So you can edit and add, change these as you desire for your codes of practice. You cannot change them in the BS, so you cannot change them in the BS, not the BS, the British version, the UK version of the annex, and you cannot change them in the defaults. If we move on to look at the concrete, you will see that for whatever code, and we're going to stick with our UK code that we're using, you have all the different alpha values and the gamma values, your 1.5 and 1.15s for your concrete and your steel. If you wanted to make that more onerous, you could put it up to 1.2. You have your K values for deflections. You have your other K values here for your design of concrete, and you have your shear component values. So all these are available for you to go in and input and modify as you desire. Now, while I'm here, the reason I brought you in here is because the concrete grades, we can input our concrete grades, and now we actually input the SCU values, but that automatically gives you the FCK values with it because it's typed out. But more importantly, you can input your FY values. So by default, I have in here 500B and 500H. I don't have 500A or 500C. If I wanted to add them, I can just come along, copy, and pop in 500C. So the number, the 500, is the yield stress of the steel, and the letter is the designator for the subgrade, and it is the letter used for the reinforcement bars. So you'll have not T16s, you'll have B16s or C16s. Now, it is recommended that you don't use H. H is the general 500 grade, and H says use A, B, or C of the steel grades. But the problem there is that if you use 500A, 500A is not great at yielding. So if you're doing any plastic redistribution or anything like that, it's not recommended. Its elongation is very, very poor. So, and then we have our nominal grade. So I'm just going to come out here, saving this with that modification, exit using current settings. Yes. And now I'm going to go back into my frame, and there's my frame again. And obviously we can also go straight to recent to grab that file again. And now we're going to ask to design. What I'm going to do first of all is I'm going to delete any sign of any concrete. So we're going to start from scratch, totally fresh, totally new. And we'll now walk into the design. And because it's new, it's going to ask me to set up the parameters. Now the nice thing is that it's going to bring the parameters in from the previous session. So whatever I did previously will be remembered. I can also go and import and load a default file. So I could go in and find a default file and import that. So I can have a set of defaults set up with all these parameters ready to go. So walking through, let's look at this. I'm going to use EC2 and for scheduling 8666, high yield deform type 2, and we're going to go for 500B rebar in the main steel and the links. Interestingly, you can't really use 250 bars, and I know that it's hard to get these days, but some people still think they prefer to use round bars, 250 bars for links. The EuroCode is not designed for 250 bars. It's only designed for reinforcing between 400 and 600 newtons per millimeter square. So really you shouldn't be using any mild steel at all. So for concrete beams, we're going to go for 3240 concrete, and we'll just go through very, very quickly, and we will not look at every single component here. And let me see, laps and cranks. We won't worry about laps and cranks. We'll just let them look after themselves, and we'll come back to them if we need to. Auto design, we're going to go for anything from 16s up to 32s. And we're going for anything from 4 to 8 bars. So we're pre-setting our limits for automatic design. In the columns, we're going to go for anything from 12s with links as our minimum, 10s, and we'll go up to 32s again. And foundations, sounds fine to me. Cover, we're going to work with 30 cover to our concrete for our beams, and we're going to add in an offset when it comes in the opposite direction. That means we drop the reinforcement when there's reinforcement coming in the opposite direction, in the other direction. So columns 30 millimeters, but for pads, strangely he's got 75 top. I would have thought it would have been 75 bottom. So whoever who was playing with this and talking last time changed it. So we could go back now and resave that, and we'll call it concrete defaults. Yep, that's just the standard one. I'm not creating any more. And for the columns, we're going to use the same concrete, and we're going to assume that they're braced, and we will use BS table 3.19 for calculating L0. This is the recommendation in the concise EuroCode, and we'll do biaxial bending to the simplified equations rather than going overboard. And we just say, okay, let's go with this. So what's going to happen now is it's going to go through and attempt to design all these members, make an initial preliminary design based on what we've set up. We can see our first member. First member has obviously got this huge big moment coming through from the big span, from the support. But the first thing you'll notice if you're familiar with BS design is it doesn't look the same. And if I go to a typical member up here in the middle, out of the way, doing nothing special, you will see we have these weird little shapes. This is not a bending moment diagram anymore. In the BS, you dealt with bending moment diagrams. In the EuroCode, you're curtailed to your tension, force, and capacity. So we have the light blue, or the bright blue, is your FT elastic. The darker blue is the FT with shear drag, and this is the big introduction that is totally different to the BS, is this concept of shear drag. And the shear drag is not a horizontal drag, it's a vertical drag. It's saying at this point here, we need to add in a component of tension for the shear drag. That is the tensile force in the shear truss. So your shear design is a truss analysis now, and we'll see that in a minute. And for that to work, we have this additional shear drag. So you can see here it's quite significant. Now the only nice thing is that they say, well, you can never get any higher than the maximum force. So that's why we get this cap. We don't keep dragging up and up and up and up. It is curtailed, it's capped, thank goodness. Now, the second thing you'll notice is that we have these tapered capacity lines. And the tapering is due to the fact that we're moving from here over to here. We're beginning to take up the effect of these thick bars, these big 32 bars. And we're using both our 3 sets of bars up to about here. And then we're beginning to lose the effect of the B16, the nominal reinforcement. So that's your B16 coming back off, and that's your main bars coming on. And this is because in the EuroCode everything's gradual, not a straight cut off as it was in the EuroCode, which is quite nice because it does allow you to sculpt things in tighter into your diagrams. So that's the next big change. Okay, so let's look at how we use the program. Very, very simple. All the information is in front of you, and the information is telling me that this beam is failing. It's telling me it's failing because we've got this red area. The capacity is encroaching on the applied, so we need to put in more reinforcement. So what I would do is I would just highlight, and then using the left and right mouse buttons on my mouse, I just go right button to go down, left button to go up. So 220s and 220s. So you could say, well, actually, let's just make that 420s. And there you go. That now works, and it works with no errors whatsoever. And you can walk along and do the same for the next member. Luckily for the next member it works, and the next member works automatically, and the next member works. And just works and no more. So we can walk through all our beams and quickly scan for any failures. So the next thing I was talking about was this shear design. And the shear design in the EuroCode is quite different. If I go and look at my results and I come down to shear, we're seeing that obviously we got a quick check against our maximum permissibles and the maximum applied, so we're okay. And then we're looking at our nominal zone. There's no real difference there to the BS. But what we're doing is, in the BS, we took the concrete resistance, and we took the steel resistance, the main steel, and the links. It's not the same in the EuroCode. In the EuroCode, your capacity is the lesser of the concrete and tension reinforcement or the shear reinforcement. You don't combine everything together. So you actually have to be sometimes a bit more generous on your links. It's a wee bit complicated. And then we have this thing called cot theta that comes into it. The default is 2.5. You do have the option in our defaults to come back in again and tell it that for design cot theta we wish to use 2.5, or we used to use a different value. If we put it down to 0.01, that is telling us, as a flag, and that tells us calculate it every time, because the value of cot theta can only be between 1 and 2.5. So by setting it down to 0.01, it's telling the program go and calculate it each time, but obviously still keep it inside those two limits. But I'm quite happy to use the standard 2.5. Okay, and we say okay. So coming back to our design, just turn off our results. We've seen that we can change the number of bars by left and mouse button. We can also change the curtailment. We can come and highlight a bar, and we move a bar by highlighting its label and then dragging it. So I can see, oh, I could pull those back. And I could also say, well, maybe in this case, he's got it wrong. I want 4 bars and I want them to be 420s. And you can see that they're okay up here, but they're no good here. So, and they're no good when we lose this. We get this failure in this zone. So if you pull this back out of the way to see it clearer, I need to lengthen this first, and then I will be able to pull this back out. You'll see that when the 420s are on their own, they're failing, and that's why we were putting the additional bars, the thickness of the bars in and everything. So what could we do to solve this? Well, we could go back to 20s and 24s, or sorry, 20s and 25s, or 25s in total, or we could redistribute. And that's one of the beautiful things about our concrete design. We don't expect you to go in and do an analysis and say, hey, let's redistribute here everything at 30%. No, you only redistribute what you need. And that's the way it actually will work in reality, because in reality, if you don't have enough reinforcement at this point, when we get up to this loading, it will start to rotate as a plastic hinge. So all I need to do is come along to my brief, to my data, and I could say at the right hand support I want to redistribute by 5. Sorry, going the wrong way. 5, 10%. So you can see we've now have an additional line. We have our elastic and our redistributive force capacity. So that's the elastic, and we've redistributed down, which has had no effect on the sagging moment, thank goodness, because we haven't gone that drastic. But we've now managed to make that work with B20s instead of B25s. And we would just repeat the same on the other side. Although we're seeing here that we've probably got higher moments. So obviously we're getting a moment transfer into the column, which we'll be looking at quite significantly. So the 420s is a wee bit tight on this side. Perhaps we could redistribute significantly. At 10% we're still not working, but we do have the scope to go up to 15, 20, even 30. So now we've gone to 20%. We're pushing the envelope here. We're right on the money. The sagging moment has physically now started to drop, but in this case we've got away with it. In other cases you might say, no, we have to go back up and put in the B20s. So you can see it's very, very editable, very, very flexible and controllable, which is great. The fact we've got 2 separate bars means that we can also be very pernickety, and if we really wanted to, we could stop one earlier than others. So we're actually getting a double kick here from one being lost and the other being lost and been taken up. In this case, that probably doesn't really make much sense because you'd end up with only having 2 bars here and it would get a bit annoyed in this zone. So I'm going to put it back out again, make it the same. So that's your beam design, except for one last thing, and that's the deflections. If I go back to my results, I can look down and see that for deflections we are looking at our stresses and we are using the concise EuroCode section 15.7 to determine our span over effective depth ratios. So it's a very, very accurate method of doing that. And I'll just close that. So coming back to our first member, or our second member, we can see here we've got very heavy reinforcement. We're into possibly putting in additional reinforcement there, and we really want to just walk through and check that everything works. Everything appears to be working elsewhere, and we can see here, we're just ever so slightly here, so we'll put in the 20s at that point and walk through and come along. And we can also ask the program to run through and find them for me. So there is a button, if I can remember where it is, find next failing member. So it'll walk through and keep going till it says, nope, don't like this one. And in this case, it's actually looking at the lapse. And that's something I was ignoring. And I was ignoring it in that this little bar here had turned cyan. And it's not because I got a failure in the capacities or anything like that. It's fact that we end up that we don't have the right width of bars. So if I go, or I have too many bars, if I go to my output, I can see the bottom right lap is greater than 170. We have 170 mil of bars with only 160 permitted. I think it's 40% width. So if I'm looking here, I've got 20s lapping on to 20s and 25s. So I could say, well, drop that down and everything works. And that's the solution to that. Now, our other alternative, there are two alternatives. One is to lift our bars up or to crank our bars, or we can even ask it to lift the bottom bars. But more importantly, what I could do is I could go in and just put that into a different layer. I can move it up so it's sitting over the top if I had to make that work. But in this case, 16s is going to do the job for me. Now I'm not going to go through and design every single beam. I don't have time to do all that. What I want to quickly move on to is the columns. And there are two ways of designing columns. Thank goodness there's the simplified way and there's the more exact. The more exact gets really hairy with your biaxial moments in 3D frames. In this case it's all uniaxial, so it's all pretty straightforward working out the section capacity. And we will look shortly at a 3D frame where we're going to get biaxial moments coming into play. So everything there is all pretty straightforward and there's no real problems. And then we have our pad foundations, and it always takes, if you think here we have 4B16s, and then look at the pad, we have the 4B16s coming in. So we have the 8B16s because there were corner bars and internal bars. So there's 8 bars. So it automatically takes the reinforcement through. If we look at this beam as well, you will see that it has shown here the column that's coming through. If we go in here, we have our reinforcement. So it's going to look after itself now. So, but we can also take our design and we can export it. We can export it to printer. So export details to printer, We'll not worry with anything else. We'll continue, and we'll just export them all, and we'll just say yeah, print, and we'll go landscape, PDF, and we'll just print those out. So now it's created 44 pages for 44 elements, and I can just close that, close that. It's building the PDF document now. So, and in this case it's got a watermark on it, which I wasn't expecting because I've been playing with something. So it's a registered dealer's copy. I've got the wrong title block. I've got a dealer's copy of the software at the minute. So it does put this watermark on. But you can see that each of the beams and each of the columns and then each of the pads is exported out automatically. And if you look, all the bar marks are incrementing up as we go, and that would have matched that schedule. So that's the first method of output. The second method, that's the DXF file. This is great, and it's what you really want to do these days, at least. Although the paper output can be useful for small work, and I'm going to go for bar mark 1 as my starter, but I'm going to go for unique bar marks for each run. What that means is I'm going to say let's start at an even number each time, and you'll see what I mean in a minute as I export the whole drawing. And I'm just going to change where that's going to export to, and I'm going to export it over the top of that one, but I'm going to call it example 1A. So it's a totally new name, and I'm going to go export, and it's told to load AutoCAD because it knows where AutoCAD is. Okay. And there we go. So zoom in, and we will see our first beam run, and just zoom in quite tight, is scheduled out with B1601s, B32s, 07s. Your links are 05s and there 13s and 12s been reused. And when we come up to the second level, it doesn't reuse them. It starts at bar mark 40, so it starts at 40, even though the last bar mark on that level was 36, or yeah, 36. So it gives you these distinct breaks between them just because I asked for it, and it keeps them unique, so you're not having, even though the bars are the same in two different areas, because they're different beam runs, there'll be different marks just to make it easier to bring to site in groups and things like that. Likewise, you then have all your columns, and you have starter bars for the beams and things like that. And I think you'll find that we actually detailed, yep, starter bars. So we have to go to column 2A to see this. It shows them there, so the fabricator, the steel fabricator, the rebar fabricator knows to put them in the drawing, and they're actually just detailed over on this one. And there we go. There's the starter columns, starter bars for that column. And then finally, your pad foundations are in here. Now, I'm just going to minimize all this. I want to keep AutoCAD open, and I'm going to come back out here and look at my frame. And the one thing we didn't talk about was, do you remember the top floor was inverted T-beams? They're great. Obviously, it kind of messes around with your reinforcement in that your compression flange is not a flange, but just the web and over the supports and things like that. And if one must, one must. But more importantly, we can turn around and we can apply loading onto the beam that is loading. So what we're saying is that half the load goes onto the left nib and half the load goes onto the right nib. We can also stipulate what your minimum is, and that's very useful to get down the amount of torsion. So it works out that it's never less than a half of that. So if we now look at our results, and this is where it will make sense, we will see that we're looking at the load and we're working out eccentricities and then working out the moments applied to the nibs. We then check our nib capacity, we check our links and tension, and we look at the additional torsion developed by the nib due to the maximum and minimums, and we turn around and say, well, it ends up being a torsion of 2.7 is the out of balance torsion, and we work that out for the span, and then we do our torsional design. So we look at, we have no external torsion, we've just got nib torsion, and we're going to design that, check for it, and it's saying the unity value is 1.32. We must design for torsion and not ignore it. So therefore, blah de blah de blah, we go through and we have to deduct top and bottom 61 millimeters of reinforcement. So 61 mil is removed from the top and bottom reinforcement in the design. So you no longer have your 393 or whatever it is for your reinforcement, you have that less 61 each time for your design. Likewise, we use an AS reduction, which in this case isn't that bad, it's only 0.05 millimeters. That's an AS over SV. So you'll see now when we go into our design that our reinforcement is 743 as opposed to what it should have been without the torsion, and we get a reduced design capacity. And likewise in the shear we're using a reduced area of reinforcement. So it does this torsion very well, but it also allows us to handle these nibs very well as a post analysis. Now we could elect to put it concentric and have it all designed separately as just part of the general beam. So we could have put torsional loads onto the analysis. Now I want to come back out and look at the third output method. And the third output method is to create what we call a MasterRC drawing. Now, this AutoCAD drawing is great, but it's just lines. That's just a polyline. That's just a bit of text. Nothing. So just highlight that on its own. That's just a bit of text, nothing else. It's not an entity of any intelligence whatsoever. So you would still need to schedule that by hand or using the inbuilt scheduler previously. So the alternative is to go up to the Rolls-Royce and export as a MasterRC file, and then to export these. And what I would normally do is export one of these and one of these and maybe one of these. Now this takes a wee bit longer to import and it requires to load AutoCAD manually. So what I'm going to do is I'm not going to load AutoCAD. I'm going to take these three elements and I'm going to export them to a new location, somewhere I can find quite easy. I normally have a wee file, a directory called temp. I'm going to put it in there and we're going to call it Fred. So we're going to go out at 1 to 20 and we're just going to have a mid-span section. Oh well, no, we'll put both sections in. Why not? And we now go and export this. So this all comes out, written out to a file. AutoCAD is not loaded because we elected not to load AutoCAD, just because it takes so long. So this drawing, I can now come along and open MasterRC. I can start up MasterRC and I can elect to go A0 at 1 to 20 and set up without a border and insert a title block and just say OK. So I'll just put this way down here out of the way. So there's my little title block. And we're now going to come in, and confirm. So there's my drawing set up as my initial template. Zoom, extents. It's just the title block. Zoom, all. So that saw us right out at the extents of our drawing. So let's bring in our exported details, because normally you're going to have your detailer on a different computer to your main MasterSeries, because it's more efficient. So I'm going to say let's import, and I can say import from MasterSeries. And I'm not going to bring in one of those. I'm going to bring in what we just did, which we put into, I believe, temp, and we called it Fred. So here's the first import, and it's a beam, and it's coming in one element at a time. So it's coming in nice and slowly as it draws and creates all the bars. As you can see, it's a lot more information coming through than it would have been in that previous DXF import. And now we have our little column, which I think is a wee small column. Yeah, it's just that wee small tiny one. Oh, I think, was it the second column in? Yes, because it didn't continue. And then a typical base. So what's the real difference between these two programs? A DXF or this? I'll show you what the difference is. The difference is that these labels, now I'm actually going to switch over. This I think is configured to be on a black background. You can see I've got my beam labels 6B1603. I've got, there they are, I've got my links labeled up above, 13B1005's 350 pitch. So that's all there. And let's turn off the, it's better. That grid was driving me mad. So here's our labels, and obviously this is the torsional steel, because we've done, so there's some torsion required. Or is it deep? No, it's the deep beam. That's what it is. It's the meter deep beams that we've been designing. Our 900 deep beams have side reinforcement. As you'll see, the shallower beams don't have any side reinforcement. They don't require it. That's what it is. And you'll see in here, there's the side reinforcement in for you. So this is all great, but the important thing is this is intelligent. This is live, this is real. If I decided to take this bar and change its diameter, so master RC, and I want to change a bar diameter, manipulate a bar. I'm going to take this one. Manipulate, I think, is only moving it. Yes, that's right. We're not changing it. I can do so, and it will then update the data. Or if I stretch a bar, it'll update the data. We can, in this, we can also schedule on drawing. So new drawing, yes, new. Okay, maybe this will work properly. There we go. There's the external schedule, just to print the printer for you. You can see all the bars, and we can ask for the weights per bar and element, things like that, and the shape codes that have been used, so that people can be familiar. Now, just to show you I can do scheduling on drawing, I'm going to open a new drawing, and I believe I put it in here. This is one I did this morning when I was practicing. Oh, get rid of those grid lines again, Tommy. There we go. And there, bar the horrible yellow color scheme, is your schedule on the drawing for you to see and use, so you can do that. So that is the round trip of doing the concrete design, we've been looking at plane frames, and I'm sorry I ran over a wee bit again. You'll blame AutoCAD as usual. I did mention that we also have the ability to do it in 3D frames. So just to prove that I'm not lying, I'm going to go back in here, choose a new another frame, and we can take a small 3D frame, which is actually the same frame just made into 3D, or we could take a huge big frame. Let's go into this huge big monster of a frame that was done in concrete. I believe it's up in Edinburgh somewhere. And it's actually several stories of concrete and then a top story in steelwork with some steel around the facade. And we can see as I zoom in that in fact we have upturned beams in this direction for some weird reason, but we have normal beams over here. So if I went into design, it's no different. It's the same concept. It's just that it's bigger. Get it? And actually, just you can see here we're now into this steel beam or this concrete frame, and then we have our upstand L beams, and we have our columns. If I can pick one of them, so you know, the full design, and oh, circular column, that's nice. In here, so that's all doable. If you go back to the website, you can just log in with your credentials, which you will have as a user, or if you're a guest trying the software, you'll have a 30-day or 28-day credentials, and you do have technical notes, you have the manuals, but you also have the training videos, and that's where this is going to be posted up to, hopefully, in the next day or so. So you have all these videos. So there's the one that was done there just for Christmas on BIM integration with Revit. Is MasterRC compatible with AutoCAD Lite? No. MasterRC requires full AutoCAD 10 to 14. If you only want to export the DXF file, the more primitive, that second method, then yes, AutoCAD Lite or any CAD you want would work. So, ladies and gentlemen, I'd like to thank you all for coming along and wish you a good day.